All right, so this is section 9.4. So the first test that we're going to talk about today, if we can use this test, this is always I think it's one of the easiest, one of the nicest tests to use, because it's not very complicated. I think it's an easy concept to understand, so that makes it I don't know, just for some reason this particular test is very appealing to me. So the test that we're going to start off talking about is the direct comparison. So now that we have some tools, we have a family of series, some families of series that we know either converge or diverge. That's when the direct comparison test becomes useful, because we know certain series that converge, we know certain series that diverge. So this lets us compare those series to other series. So our direct comparison test, our conditions, we're going to say that we're going to let 0 be less than the terms of some series A sub n and another series B sub n. So we have this inequality, and this is true for all n. We have two conditions for the direct comparison test. If the infinite series n equals 1 to infinity of B sub n converges, then the series for A sub n converges also. And the second condition we're going to look at is if A sub n, the series for A sub n diverges, that should be then so does the series for B sub n, the sum for B sub n. So this is our direct comparison test, and I think of this one kind of graphically. If we have one series where the terms are always greater than another series, and the series with the greater terms converges, I think of it kind of pushing down on the series with the smaller terms. So the greater series puts a bound on the limit, it kind of pushes it down. And if the lower the series with the terms that are less, if it diverges, it's pushing the other series up. So we have to, when we use the direct comparison test, we have to make sure that we're making that our series, the terms of our series, compare the way we want them to. It's an easy mistake to make to assume that our inequalities are working the way we want to when they don't. So and that the kind of graphical argument that I just made, that's how we would go about proving this test. If for this first condition, if the series, if this sum for B sub n converges, that puts an upper bound on the sequence of partial sums for the series for A sub n. So that ensures that A sub n converges. And the second case, because A sub n diverges, the series for a sub n diverges, the sequence of partial sums for b sub n is going to be unbounded, because b sub n is always greater than a sub n. So that's how we would go about proving those. It's pretty intuitive idea using the direct comparison test. So let's look at a couple of examples, and then this will lead us to a little bit of a problem, and then we'll talk about another test. So we want to test for convergence. That's what we're doing here. We want the sum n equals 1 to infinity of 1 over n times n plus 1 times n plus 2. So looking at this, what's one tool that we could possibly use on this series? Partial fractions. This could be looks like a telescoping series. So we could use partial fractions. We could probably find the sum, or determine if this converges or diverges using partial fractions. Well, this one wouldn't be too bad, but depending on your fraction, the partial fraction decomposition can get, just algebraically, it can get kind of ugly. But what I'm going to say is that 1 over n times n plus 1 times n plus 2 is less than 1 over n to the third. We all agree on that? And the sum, n equals 1 to infinity of 1 over n to the third is what? What's that?
Oh, yeah.
We're dividing by a bigger number. Our denominator is going to be bigger here, so our fraction is less, right? Sum from n equals 1 to infinity of 1 over n to the third is what? What kind of series? P series. This is a P series with P equals 3. So this is a convergent or divergent P series? Convergent. P is greater than 1. So this is a convergent P series. So each term of the series that we're interested in is less than each term of a convergent series. So the series converges by direct comparison.
So if you accidentally compared it to a series that was greater, like if 1 over n cubed diverged, then you just wouldn't be able to.
You wouldn't be able to make this argument, right? You might be able to find a different series to compare it with, but if the greater series, the series with the greater terms, is divergent, it doesn't tell you anything about the series with the smaller terms. This one goes here. This one could do all kinds of things in between. It could converge, it could diverge, but we don't know. So this series converges by direct comparison. And that mistake that you just asked about, Katie, that's the one that's easy to make. That, oh, this series diverges, so this one has to diverge. But we can't, because this series has greater terms. It doesn't really tell us, if it diverges, it doesn't tell us anything about what's going on underneath it. All right, let's look at another one. We want to look at the sum n equals 1 to infinity of 1 over.
Are we always going to make the series that we're comparing smaller series?
Well, if we want to show that it diverges, we have to show that the terms are greater than a divergent series. Greater than the terms of the divergent series. So if we want to go the other way, we have to find a divergent series whose terms are less than the series that we're interested in, the terms of the series we're interested in. So we want to determine the convergence of this series. Anybody have an idea of how we might go about this? Anybody have an idea of what we might want to compare this with? All right, I'm going to say that 1 over, and that's a hard part about the direct comparison, is figuring out what to compare it with. But as you get some more experience, you'll start getting better at it. I'm going to say that 1 over square root of 2n minus 1 is greater than 1 over square root of 2n. We all agree on that? And this is for n greater than or equal to 1. And 1 over square root of 2n equals 1 over the square root of 2 times 1 over square root of n. So I'm going to say this is 1 over the square root of 2, n equals 1 to infinity of 1 over square root of n. And what kind of series is this? P series. And it converges or diverges? Diverges because P is 1/2. So this series diverges. Our terms are greater than the terms of a divergent P series, so the series diverges by direct comparison. So direct comparison is nice. It's a very nice test to use. The hard part can be figuring out what series to compare it with.
So in the inequality you wrote, the incident is always the one you compare it to, not the
It depends. Depends on whether you're trying to show it's convergent or divergent.
Because this one you're saying that, alright, they can still up.
Okay, does that make sense? All right, so let's look at where we might need to do something a little different. Where we run into a problem similar to one we talked about earlier. Let's look at the general harmonic series. So we want to look at the sum, n equals 1 to infinity, of the general harmonic series has a form an plus b, where a is greater than 0 and b is greater than 0. Now it would be very tempting. What if we were looking at this? What do you think we would want to do here? We know the harmonic series diverges, right? So if we could show that this is greater than 1 over n, we could argue by direct comparison that the term by term, this is greater than 1 over n by direct comparison. But is 1 over an plus b, how does that compare to 1 over n? It's less than. So we can't use direct comparison with the harmonic series. But it seems to make sense that if the harmonic series diverges, this would diverge. And we should be able to compare it somehow. So we can't use direct comparison test here. Yes, ma'am. But looking at this, it makes sense that if this diverges, this needs to diverge as well. They're not that much different. So let's look at another test that will allow us to compare these two in a way.
Don't they both diverge?
They both diverge, but we want to prove that this diverges somehow. Okay. What's another way we could possibly prove that this diverges? What test have we used that we could? What do you think, Ian? Okay, so and that's why it would make sense that this diverges. He's saying, Liam says factor out an A, and basically this is just the harmonic series shifted. So, but we want to somehow prove that this diverges analytically. Does anybody think of another test that we could use possibly on this? Well, that's where we're going. Pretend we haven't learned those yet. One that we have learned. We could try the integral test. We could try the integral test on this, and that could work possibly. So that's another test we could try. But let's look at another one. To me, there's something appealing about this. Somehow relating this to the harmonic series. So we're going to look at the limit comparison test. So when we get something like this, to me that it suggests that there's something, that we're close to something. We just haven't quite found it yet. And the limit comparison test can be what we're looking for. So for the limit comparison test, we have a sub n greater than 0 and b sub n greater than 0. So we have positive terms. And our other condition for the limit comparison test is that the limit as n approaches infinity of a sub n over b sub n equals some limit where L is finite and positive. So the terms of our series are greater than 0, and the limit as n approaches infinity of a sub n over b sub n is some finite positive limit. Then we can conclude that the series for a sub n and the series for b sub n either both converge or both diverge. So this could possibly give us what we want, the comparison that we want up here. We know that the harmonic series diverges, so we could use a limit comparison test with a general harmonic series and the harmonic series and show that this limit is finite and positive. Then we can show that the general harmonic series diverges. Let me quickly. Did I? Okay. I thought I misspelled something. The proof is very short and simple here for the limit comparison test. Our proof is, since we know a sub n is greater than 0 and b sub n is greater than 0, and our limit is L, we have, by the definition of a limit, there's a some n, or sorry, capital N, some n greater than 0, such that 0 less than a sub n over b sub n less than L plus 1 for n greater than capital N, greater than or equal. This is just the definition of the limit. So for some n greater than 0, eventually we get to, if we take our terms out far enough, we get that this ratio is less than L plus 1. So we're taking out enough terms, so this ratio is less than L plus 1. So my inequality, I can rewrite this inequality. So 0 is less than a sub n, which is less than L plus 1 times b sub n. And so if b sub n converges, then a sub n is also going to converge. And if a sub n diverges by the direct comparison test, if a sub n diverges, then b sub n, the series for b sub n is also going to diverge. So the proof just involves a definition of the limit. So pretty simple proof. So let's go back to our general harmonic series and the harmonic series and use the limit comparison test. For the general harmonic series, we're going to look at the limit as n approaches infinity of 1 over an plus b over 1 over n. And if I rearrange that, I get the limit as n approaches infinity of n over an plus b. And what's that limit? 1 over a, which is greater than 0 and finite. So the series diverges. By limit comparison. If it equals 0, there's no conclusion. You have to use another text. So or you could compare it to a different series. Yeah, you have to do something different. If the limit equals 0 or is undefined, then there's no conclusion from the text. Yeah.
Did you say that on the last page you had inequality,
Mm-hmm.
and it was 0, which is less than a span, which is less than L plus 1, which is 0, right? And you said that if a span that
Diverges.
then b span diverges.
Right.
But not the other way.
If b sub n converges,
Yeah.
then a sub n has to
But
converge.
if b sub n diverges, then you have to get it.
Right, and then so there's another part of the proof that I didn't show you for that condition.
Okay.
So this shows this shows basically
That's what
it shows basically half of what we claimed, right? It shows for one direction for one series and another direction for the other series. There's another part of the proof that shows that the other conditions are true. So this isn't 100% of the proof. Nice observation. All right. So we have a direct comparison. We figured out a direct comparison test. We have talked about our limit comparison test. The limit comparison test is very nice for a certain type of series. One, like we just talked about, where the two series seem so similar that there has to be a way to compare them. But if we have something like the sum n equals 1 to infinity of 3n squared plus n over n to the fourth plus the square root of n. And we want to determine the convergence or divergence of this. This is kind of messy. What's that? N to the fourth. Yeah, this is messy. To use other kinds of tests to analyze this somehow could be very messy. The algebra could get very messy. So what I'm going to do is say that the highest power in the numerator is n squared. So we have n squared, and in the denominator is n to the fourth. So I'm going to compare this with n squared over n to the fourth. Which is just 1 over n squared. And what kind of series is this? Convergent P series? So what I do with something that's where I have these polynomial terms, these algebraic terms where I have powers of n, I just pick the highest power in the numerator, highest power in the denominator, and I'm going to compare this series with the similar series written just with the highest power in the numerator and highest power in the denominator. So this is a convergent P series. So I am going to say that a sub n, my a sub n is this fraction, and my b sub n is this fraction. So I'm going to look at the limit as n approaches infinity. I'm going to use the limit comparison test of 3n squared plus n over n to the fourth plus square root of n. And I'm dividing by 1 over n squared, so I'm going to just rewrite that as multiplication. And if I simplify that, n approaches infinity of when I distribute 3n to the fourth plus n squared over n cubed, thank you, over n to the fourth plus square root of n. And how can I, now what can I do here? L'Hopital's rule, and this equals 3. That limit equals 3. So I turn this problem into a problem of figuring out a sum into a problem of figuring out a limit, which in this case for series or for terms that look like this with powers of n is much easier. I just take.
So like we can just say that it's like you don't have to actually show it.
No, you could say by L'Hopital's rule this is 3. And the other trick you can use on limits like this, if you do L'Hopital's 4 times, yeah. The other thing you can do with terms like this is I can divide everything in the numerator and denominator by the highest power of n. So if I divide everything in the numerator and denominator by highest power of n, I get 3 plus 1 over n in the numerator, and 1 plus square root of n divided by n to the fourth, whatever that is as a rational power, and take the limit as n approaches infinity, and all that's left is the 3 and the 1. 3 in the numerator and the 1 in the denominator. So that's another way you can analyze limits like this. Divide everything in the numerator and denominator by the highest power of n, and then take the limit. And that works nicely also. Kind of the same idea as using L'Hopital's. So anyway, our limit is finite and positive, so the series converges. By limit comparison. And the other argument you could use on a function like this is this. I guess this isn't exactly a rational function because of this square root of n. But if you have a rational function, you know that the horizontal asymptote, if the powers in the highest power in the numerator and the denominator are the same, the horizontal asymptote is the ratio of the leading coefficients. So that's 3 different ways we could talk about something that looks like a rational function. All right, questions on limit comparison and direct comparison? Okay. There you go.